Hello everybody, my name is Liang San. Today I will give this presentation on this work, real-time moving horizon estimation for an aerial towed cable system. This is the outline of my presentation today. So first I will talk about the overview of unmanned aircraft system, we call it UAS. And after that, I will talk about this project we are focusing on. It's called aerial recovery. So after that, we'll talk about this moving horizon estimation for the this towed cable system. In that, we'll talk about the motivation for this moving horizon estimation and the formulation of the problem. Also, some challenges in the real-time flight test. And at the end, we will show some flight test results and also some offline results. And we will give this conclusion and future work at the end. Okay, some of you may not very familiar with the UAS, the unmanned aerial system. So basically, we can classify the UAS into the fixed wing, like the upper two figures, also the hovercraft, the lower two figures. So the fixed wing is typically can fly very fast, and the airspeed cannot. They have some range. They have some lower limit for the airspeed. But for the hovercraft, that we can slow down the aircraft, even make it hovering in the air. So for this hovercraft, we usually use them in some indoor applications. Like the lower left figure, that is quad rotors. They have 4 rotors, and we can see some markers on that. That's used for to localize it indoor. Use some other camera-based, we call that motion analysis system. The lower right figure is a very beautiful construction which built by the Colorado. I will show the videos later. Let's look at this video. This video is, so you can see the red lights here on the ceiling of this roof. So there are the cameras can capture the markers on the Colorado, can know its attitude and position, so they can control the Colorado. So this video is for some aggressive flight, and they can go through the window with very quick airspeed. And this one is the video for the using the Colorado to build some constructions. So there's cameras on the bottom of the Colorado. They can see where they are, and use the computers to control them, to deliver these bricks. This is very nice applications. The last one is a nano controllers. So they are very small, and you can throw them and launch them. They can hover in there. There they go. So the most amazing is that formation control. So there's 20 this nano controllers. They can fly in together and make different shapes. So they can also fly in a 8-figure pattern. You can see small one here. The collaborative control use a computer. And so okay, next I will talk about this aerial recovery project I'm working on. This project trying to answer this question. So how can we retrieve these miniature aerial vehicles, we call them MAVs, in the air after they complete their missions? The basic scenario for this project is that we launch multiple MAVs from one large airplane and to do their work. So after they complete their missions, they may not have enough fuel to return home by themselves. So how can we get them back? Use some other aircraft. So here are some retrieval methods used by used in the literature. So first one, the upper two figures is for the fixed wing retrieval. So first one, they use parachute. The basic idea is to after the MAVs run out of power, they use parachute just go with the wind. So the uncertainty will kill this method in the most of cases. So the upper right figure shows a retrieval mechanics. They use a hook device on the MAV, which can be captured by a string on the ship or other vehicles. So this one will require the MAV can get close to this device first, but that's not the case in the aerial recovery. The lower two figures are the method for retrieval the hovercraft. The lower left one is the one used on the ship. So some UAS, so that the hovercraft can return home by themselves. So, and the lower left one is very interesting one. They use unmanned ground vehicle. We call that UGV. So they use UGV to launch this UAV and UAS, and after they complete that mission, they can coming back and landing on this UGV again, recharge, reland, and relaunch again, and that's the basic idea. The drawbacks of this that we need a UGV, and how should we control that? That is more complex thing. For this aerial recovery project, we use this towed cable system. That basically have three components. First is the large airplane, we call that mothership, with a long cable and dragging a jog. The basic theory for this system is that if the mothership flying in a circular orbit with radius capital R, and in this steady state, if the jog has enough drag coefficient, aerodynamic drag, the orbit of the jog will also be a circular, and the radius of that orbit will be much smaller than the mothership. So since the angular rate of both the mothership and jog are the same, the airspeed of the jog will be much smaller than the mothership, which can be matched by the MAV. So the MAV can get close to the jog and capture by the jog. So that's the basic idea of this project. And in the flight test, we use this communication structure. So basically, we have four components. Besides the airplanes, the UAS in the air, we have a ground station. The ground station consists of a computer which runs the software. We call that virtual cockpit. And the computer connects to the comm box, which talking to the modems on the aircraft. The modems will talking to the autopilots, which will control the UAVs, and the MAVs here we call that seeker UAS. It has more components on it. They have a camera at the nose of that UAV, and they also have a video process unit we call the VPU, and also they can send the video through the video transmitter to another unit on the ground station called video receiver, which can send back the video and record it on that computer. We also can connect the MATLAB and the virtual cockpit through this max function. So we can design our control law inside MATLAB and send and receive that command through the virtual cockpit and to the airplanes. Here's some figures for the hardwares we use. The first one is the mothership. The wingspan is about 1.5 meters, and they have two motors which can give more power to drag both the cable and joke. And the upper right one is the autopilot. We use all three aircraft systems. And the lower left figure is the joke we use in this preliminary flight test. That is a hemisphere. The diameter is about 30 centimeters. They have autopilot modem GPS unit in there. And the lower right one is the cable. It's a fishing line, can hold 20 pounds payload. And currently we use 100 meters cable. 85 meters cable in the real flight test. So this figure shows the top-down view with left figure, and the side view on the right in presence of the wind. And we can see that even though the mothership orbit is flat, the horizontal view of the joke orbit will be shaped to the direction of the wind. So the wind is coming from the east. So we can see the steady state orbit of the joke is shifting to the west. And also the side view, we can see that the joke orbit will not be flat anymore. It will be inclined. So the deviation here we can see is within 30 meters. So that is not good for the MAV to follow that inclined orbit. So my part of work is focusing on how can we maneuvering the mothership to give a flat joke orbit. So here are some results we have got, and we based on the dynamics of the cable joke system, we can calculate a trajectory for the mothership, which can give a flat joke orbit. So this figure shows the top-down view, side view on the top of the this control method. So we can see by maneuvering the mothership, the deviation of the joke orbit can be narrowed down around 10 meters. And also, we can control the mothership following its airspeed and altitude in the real flight test very well. And here I will introduce this dynamics model we use for the cable. So we divide it into multiple links. So every link is a rigid rod we cannot bend. So they connect by this joint, which is a red dot in there. So every link we consider them as springs, so they can stretch. Okay, after talk about the error recovery, I will talk about this moving horizon estimation. The motivation for use this moving horizon estimation in the error recovery is that first the whole system, the mothership, cable, joke, it's a very complex, non-linear, non-rigid body, non-rigid system since the cable is soft. So we have a lot of parameters that we cannot measure. So like the spring constant of the cable during the flight, also the aerodynamic coefficient of the joke, also some other disturbance like the wind estimation is not estimated well using the current software. So we want to estimate that because we want to use the wind estimation to calculate the trajectory for the mothership. And another application is that sometimes and almost always we have the problems of losing the GPS signals. And that is very significant in the final phase of this aerial recovery. So we want to figure out a way to deal with that, even the GPS is lost. So that's the motivation for moon horizon estimation. And for this part, we can talk about the formulation of this problem. We will use the F1 norm object function in it. First, we want to implement this moon horizon estimation in the real flight test. So there's some challenges in this real-time application. So first is the communication lags. So GPS talking to the ground station and also the modem. So we have a communication lag that is cannot be solved. And also this is three agents in the air. So there's the bandwidth problem is always there. So the communication lags is something we need to consider. The second is that this moving horizon is optimization method based. So the computation time should be considered. And based on our ground station, the computation time can be narrowed down to less than 0.1 seconds. And the step size we choose is 1 second. So the computation time is much smaller than step size. That means for one calculation that is can be complete within one step. And also the calibration is very important for this system, since the mothership and joke they have two separated GPS. So we have to unify the home position for different autopilots to get a enough accurate position. And also in the future work, if we want to use some results from the APMonitor to control the mothership or joke, that means we have to guarantee the solution is successful. That we can use that to control. So that may other things we need to think about for the solution reliability. So I'm holding this mothership and try to launch that. We tried many times to launch this system with 100 meters cable. So right now we are trying to do a one loop. So the mothership and joke will stay in the same side, and the cable is go forth and coming back. So can be launched very well. And this is a figure from the website interface of the APMonitor. So this blue line is the altitude of the joke we got from the model, and the orange line is the real altitude of the joke from the flight test, and the black one is the dead band. So we can see that the model value is matched the real value is very well. Estimation of the joke length, the cable length, and this is the panel of the ground station software. We call that the virtual cockpit. We can see that the green The green orbit is the mothership. The yellow one is the joke. So currently we fly that in a orbit of radius of 250 meters, and we can tilt this this graph and see. Oh, I said it wrong. The yellow one is the orbit of the mothership. Green one is the joke. So the joke altitude is lower than the mothership. And we also try to estimate the wind components in the z direction, which point to the down, and that works very well as well. So we also try this smaller orbit, which is 150 meters radius, and to see whether they give us the similar results. And it turns out it works very well.
This is the main window for the virtual cockpit we use in the ground station. So this software is developed by the Perseus. So on the left window, the first is the UAV modes. So we can switch between different modes to command the UAV. And next is the agent list. We have, if we have multi-agents, we have multiple lines. So each lines we have the agent number, the colors for this agent, the battery volts, the communication strength, current altitude, airspeed, GPS signal, and we can switch the remote controller between different modes. And this window is the heading up attitude window, so we can see the attitude of the UAV. And the next window is called message window. So we can see we can no com, or we lost GPS, or the altitude is too low. So there will be warnings showing up in this window. So the last line is the pre-flight tools. So we can zero pressure every sensors, etc. On the right side, they are the main window here. So we can see this is the local map of the flight test you are working on. You can drag to see different maps. You can zoom in and also zoom out. Here is the ground station, the home position. So this is the wind estimation, the direction and magnitude. Also the gimbal, the uh, the gimbal information, also the attitude information. So here is the window to set up the configuration of different mode or different waypoint. Like if we insert 4 waypoints, their information is there. We can configure them here. Also, we can insert a locator. So we can double click that, change everything here, or change everything here to that same. And red, they have a window can override the altitude and airspeed. Okay, I will delete them. So just click that, delete them. I will replay. They have a very useful tool which called replay. So if you have store the flight test logs, so we can replay that, use all the information there. So here's a mothership flight test log. So we command is flying in a circular orbit in the clockwise direction. So you can see this window showing up the current altitude, roll page R for the current agent. We can see the altitude is changing while it's flight. The wind estimation is 1.2 meters per second, and this gimbal represent the headings. And
Results we get from the flight test. So first figure, we use the model of two links. So the the blue line is the estimation, and the red line is the average of all the data. And these four figures, we use different number of links from 2, 3 to 4 and 5. So from the average, we can see they give us very similar results, about around 75 meters. And the deviation is 10 meters. So that seems that the estimation has some oscillation during the flight test. I will give a explanation later. So this is the results of the comparison of the joke altitude of both the simulation and the flight test. The blue line is the value from model. So the red one is the real position, the real joke altitude in the flight test. The black one is the dead band. So they all works very well and give us very similar results. So we calculated the difference between these two values for the joke altitude. So the average is about 0.2, is very small. The standard deviation is 3.7 meters, around that. The conclusions for that. So first we can see that the real-time of moving horizon estimation for this cable system works very well in the real flight test. And in the real flight test, we use this cable is around 85 meters, but the average of the estimation of the cable length is about 75 meters. The reason is that first we use this rigid link model to simulate this cable, which may not that accurate, or the number of links may not enough to represent this cable well. Also, we can see that the curvature and the stretchiness of the cable in the real flight test is much larger than that in the simulation. And as we have talked about before, other parameters like the spring constant of the cable, the aerodynamic coefficient of the joke, also the wind estimation may not that accurate, which can give us much errors in the estimation of the joke of the cable length. So in the future work, as we talked before, we want to move forward to estimate other parameters like the spring constant of the cable, also the aerodynamic coefficient of the joke. Also, we want to try to estimate the disturbance like the wind estimation. Also, after we can handle all of that, we can move forward to the GPS denied applications. Thank you everybody for watching me.